Thank you very much. So what I'd like to do today is to tell you a little bit about if you take Fano's prescription of you can't create coherence, you shouldn't destroy it seriously, and we try to use coherence in the form of quantum information, we're going to, of course, have to invoke symmetry to preserve that information, and we'll show you some examples with magnetic resonance of how, in fact, we can try to take quantum information and do something interesting with it, hopefully something that you can't do in the classical world. I guess I won't wait, even though it asked me to. If you think about quantum computing, maybe the first thing you might ask is, why bother? What does it give you that you can't do otherwise? For this audience, maybe the most appealing thing is to think about efficient quantum simulation. That if you had a quantum computer, then we have this belief that we should be able to simulate quantum dynamics much more efficiently than we could on a classical computer. We know that simulating most quantum dynamics is a computationally hard problem on a classical computer. And of course, we know also that if we know the Hamiltonian structure, we can map that onto any quantum processor. And of course, our quantum processor would work much better than this thing. You could just stop that and continue this. And we would have seen that that we could have essentially a universal quantum simulator of our system. Now, of course, that was an old idea introduced by Feynman to look at quantum information processing. And although it got a little bit of attention, it certainly didn't get the attention of the funding agencies. And what you wanted to do to get the attention of the funding agencies to solve a problem that physicists didn't care about, but that the funding agencies cared about. And the problem for the funding agency was, of course, how do you break encryption? And so Peter Shor's factoring algorithm showed that if you had a quantum computer, you could exponentially more efficiently break codes. And hence the Defense Department, fantastic. Let me...
Quantum computer would have worked, actually.
It would have, I'm sure. Come on, Clyde. Okay, good. So we'll continue. So we've got our quantum computer, and our quantum computer we might think of as a string of nuclear spins. We're going to apply a series of quantum gates using the rules of quantum mechanics. And at the end of the day, we're going to get out a series of nuclear spins, and what will have changed is the state of those. And of course, we want to measure some aspect of that final state in order to find out what was the answer of this computation that we applied on that string of nuclear spins. Now, of course, since we're going to communicate with our quantum computer, and we mostly live in the classical world, what we anticipate is that the input state here, of course, is going to be classical, and we will put the information along some preferred basis so that we will know what the answer is, where to find the answer at the end of the day. The power of a quantum computer doesn't come, of course, from what the input states are. As I said, the input states, although we represent it in terms of spins, are classical states. The outputs are classical states, at least a part of it that we want to measure. But the algorithm that we would run to answer some problem in the classical world and in the quantum world should have different complexities, so that as we look at scaling of the size of the problem, the computational time, eventually, if we get a big enough system, should be more efficient on a quantum computer than on a classical computer. And of course, what gives us the advantages of that efficiencies are the normal quantum ideas of superposition, quantum interference, entanglement, and perhaps projective measurements. And you can imagine as a very simple example, I'm not going to go through quantum information theory for you, but you can imagine as a very simple example, if you're looking at Grover's algorithm that allows you to have a massive search, you get a huge advantage first from superposition, being able to put your input into all possible states simultaneously so you can ask all possible questions. But of course, you want to make a measurement at the end of the day. Where really Grover's algorithm gets its powers from quantum interference. It not only asks all possible questions, it filters out the final incorrect question for you as well. Okay, so we talked about this a little bit, that what a quantum computer would allow you to do is, of course, simulate quantum systems, simulate classical systems too, interestingly enough. Secure communication, so that although with decryption you have the advantage that you'll be able to break everyone else's code, quantum computing gives you back that value in that if you had one, your own codes would not be breakable by anyone. Fast searching, and perhaps, this is really an iffy thing over here, but perhaps there's an approach to solving NP-complete problems. That's very much controversial in the field, but there is an algorithm out there that appears to work. Now, how much power do you get?
What is meant by NP-complete?
The traveling salesman problem is an NP-complete problem. So that you know that, or perhaps you don't know, there's a set of computationally difficult problems that are the four-color map problem, the traveling salesman problem, finding the lowest eigenlevel of an Ising model with random couplings. And if you could solve any one of these problems, you could solve them all. That's the so-called completeness of it. And it's an old problem in computer science to try to find efficient problems, or to even prove that they're non-polynomial. And perhaps with quantum information processing we could. Okay, you say, well, how big a quantum computer do I need to do something interesting? And so what we've plotted here is the relative size of a quantum computer that would give you the same computational power as some classical computers that you might know and love from your youth. The old venerable PDP-11, which there are a few people in the room old enough to have used. And you need to grab a whole 12 atoms to have that sort of power. Now, of course, the PDP-11 is a horribly old thing. You might say, well, okay, the Cray is a horribly old thing too. But you have something like a Cray, you need to have all of 30 atoms in order to have the same computational power that you would have with a Cray, provided that you could control those 30 atoms and follow the full dynamics of them. So where we are today is that we can do quantum computations on about 10 qubits. So we're not quite up to the PDP-11, but we hope to get there someday. Okay, so how does it work in magnetic resonance? In magnetic resonance, what we do is we take a molecule where we rely upon the chemistry of the molecule to define our qubits. And so if I think about the simple molecule dibromothiophenone, there are 2 protons. And protons, of course, are spin 1/2 particles. We will map each of those protons into a quantum bit. And there's a scalar coupling between the 2 protons. And so we'll be able to do conditional operations of 1 qubit, 1 proton, based upon the states of the other. Of course, we'll take a liquid sample of this, 10 to the 18 copies of the molecule, put it into a strong magnetic field, so we have a known quantization axis, and so we can map our information onto the projection of the spin along the z-axis. We know the Hamiltonian very well, but of course we want to modify the states of the system, so we use radio frequency pulses and all the normal stuff to change the states of the system. And the advantages that we have in this system is that we know the internal Hamiltonian very precisely. We know the decoherence of the system very precisely. We know the noise generators of the system very precisely. And we have very good control over the external Hamiltonian. And so I have an external Hamiltonian with a radio frequency field. We can modulate this Hamiltonian in its strength, amplitude, phase, and frequency. And I'm not going to go over the mechanisms or how we do this, but we can create any propagator on this space, and we can do it with the precision of at least 2 nines. So that the fidelity of any propagator we want to generate on this space, or a space on up to, on a space of up to 5 qubits, we can have any arbitrary rotation with a fidelity of 0.99. So that allows us to do quantum computing. And so what we're going to do is to take our nuclear spins. We're going to use them in a quantum computer. We're going to, of course, use superpositions. We're going to use entanglement. I'm not going to go over this because it's so old hat for you. But I want to look here. Imagine that I'm trying to generate the power of quantum information. I want to create a computation that spans a large Hilbert space. If I say that entanglement is an important part of the speed up, then if I have an entangled state such as this one, I should like to preserve that state. And you can see exactly what's going to be the problem here is that we just heard that, of course, we can't copy. There's no cloning theorem, so we can't copy the state. I want to preserve it, but of course, I have decoherence going on in my system. And under decoherence, if any one of these individual spins decoheres, of course, I lose this state entirely. So these large entangled states are incredibly sensitive to decoherence. And that is a challenge of the system of how do we protect the information knowing that we can't copy it. Now, there are a variety of ways of doing this. So I start off with some spin in an arbitrary state. I would like to preserve it. And what we're going to do now is we're going to use a large number of extra qubits. Now, I can't copy the information from there to there. But what I can do is I can correlate the information on the left to these ancilla, to these well-polarized additional bits started in a known state on the right. And I will use the correlations there as a way of preserving information. In other words, I'm going to take the information here. I'm going to take additional resources. I'm going to code it into a larger Hilbert space. I'm going to use that additional expanded Hilbert space as a way of characterizing what the decoherence was on the system over some period of time. I will then decode the information, measure the ancilla, and from that measurement of the ancilla, I will know what the decoherence actually was that occurred. And hence, since I know what the action of the environment was, I can undo the action on the spin of interest without ever having known its initial state. I will put it back in that initial state. And we will, since we're experimentalists, we'll actually do this in practice. Okay, so we've got one spin, arbitrary state. I've added two ancilla. What I'm going to code against here is a simple spin flip error. I'm going to allow a spin flip to occur on the spin of interest or on any of the ancilla that I would like. And I'm going to code this information for an infinitesimal time. Okay, so I want to worry about whether no spin flip occurred or a single spin flip occurred. If we're looking at processes where multiple spin flips occurred, then of course we would have to have additional ancilla. Well, I'll talk about that in a second. But we're looking at spin flips. Now, if I have my one spin of interest, there are two errors. Did it flip or didn't it? Then I need to have two Hilbert spaces to code that information, two copies of the Hilbert space. But when I add one ancilla, then of course I've copied the Hilbert space once. I have two copies, but now I have the additional possibility that there could be an error on the ancilla. Okay, so I need again to increase the Hilbert size of the Hilbert space. And if I add a second ancilla, so now I have four copies of the Hilbert space spanned by the original spin, then I have a sufficient space to code all possible errors. A subspace for no errors, a subspace for a bit flip on the first spin, a subspace for a bit flip on the second spin, and a subspace for a bit flip on the third spin. So now I at least have enough space to code all the information. So we start off with having our unknown state, two additional spins in known states. The coding is to conditionally rotate the ancilla based upon the state of the unknown spin, or the unknown state of the spin of interest. And so we go from this product state to this entangled state. We now allow decoherence to occur. And under this decoherence, either one of these spins will flip or no spins will flip. We then decode the system with exactly the same correlating process we used to encode it. And so at the end of this decoding step, we find these are the states of the system with, if there was no error in the system, both of the ancilla are pointing up, and of course the spin is returned in the state it started off with. If the first spin flipped, well, the first spin was still flipped, but both of the ancilla are pointing down. If the second ancilla flipped, or the third ancilla, second spin flipped, or the third spin flipped, we go into orthogonal subspaces, but of course the state of the original spin is left unchanged. From here, we immediately see that there's a unitary evolution, a unitary process that would return all of the states of this original spin to its original state. All I have to do is conditionally rotate this spin by 180 degrees based upon the two ancilla being down. If I do that, then again I will have a product state where the first spin would be the same in all examples. I would have the rest of the Hilbert space, copies of that, with the probabilities that you have had any of these errors, and I can simply trace over the ancilla, collapse down into a 2 by 2 density matrix, and again I would have the full probability that the spin is in the original state. No errors would have occurred. Now, of course, by tracing over the ancilla, I've thrown away some entropy. Okay. This just says the same thing. Here's the data, and what I've shown you here is essentially the fidelity or the correlation of the initial state with the state that we prepared. This is time. Normally, what would happen is you would expect an exponential decay with time, because that would be the would just be your exponential relaxation process. And I have to worry about two different cases here. I would need to worry about having a totally correlated error, that all the spins flip at once, or an uncorrelated error. If I have an uncorrelated error on the three spins, and let's just look here at this blow up, as a function of time, and I apply quantum error correction, then we see that the initial slope there is flat. So we've gone from an exponential decay to a decay where we've suppressed the first order process. And of course, that's what we said with quantum error correction, that we would suppress the action of one error. So we remove the first order process. If I have a totally correlated relaxation, we still remove the process to first order. Of course, the shape of the higher order terms are different, but that doesn't make any difference. We've still removed the errors to first order. And if I wanted to, and we had additional resources, we could repeat this process. We could concatenate this process over and over again, remove the second order, the third order, etc., and take these curves and shift them all the way up until we had a flat response. The other thing that, of course, this nicely shows you is that quantum error correction is a wonderful way of probing the symmetries of noise generators, that the second order terms tell you exactly what those symmetries are. Now, quantum error correction, as you see, is a wonderful process because it tells you that decoherence is not a challenge in spectroscopy or in quantum information processing, provided you have control over a lot of quantum resources. Unfortunately, today, we don't have control over a lot of quantum resources. Every quantum resource costs us incredible amounts of effort. And so, although quantum error correction from an information processing point of view has said, yes, in principles, quantum computers are possible, it hasn't actually, in a practical sense, opened up a door that we didn't have before. And so what we'd like to do is to say, are there more efficient ways of controlling decoherence? And if your noise generators are not a complete set, if there's a certain symmetry to your noise, then we expect that quantum error correction is overkill, and that there should be more efficient ways of attacking decoherence. And a very simple example of that is to look at far-field noise applied to spins. And so if I have a nuclear spin, it's a magnetic dipole, you know, the only thing it's going to do is it's going to rotate in response to other fields. If I have two spins, and they both see the same far-field magnetic field, then if they're aligned together, they're going to rotate together, and the phase shift would be twice as fast, of course. If, however, they were anti-aligned, then the phase evolution of one spin would exactly cancel out the phase evolution of the second spin. And so in the case of having anti-aligned pairs of spins, they're protected from phase evolution, from decoherence, due to far-field sources. That's essentially all this says, is that if we have a spin and we're looking for a phase noise, it picks up a phase shift, of course. And if we look at the two-spin case and we restrict our phase noise to being in the far field, then the spin breaks into two subspaces. It has a double quantum subspace that rotates at twice the normal angular velocity. And it has a zero quantum subspace. And the zero quantum subspace is preserved from evolution due to this far field noise. And so in this case, we can encode our information into the zero quantum subspace, manipulate the information at all times in the zero quantum subspace, and be independent of any noise sources that we would see. And that's what we've done here. It's an incredibly simple experiment that we take our spin, which has an arbitrary state. We correlate it to one additional qubit, which was started off in a known state. In doing that, we make sure that our correlation takes us to the zero quantum subspace, essentially to a set of Bell bases, to a Bell basis spanning the zero quantum subspace. We apply noise, which is a far field noise. At the end of the day, of course, in order to make a measurement, we can't make a measurement in the zero quantum space, so we have to decode, go back to a single spin space where we can make a measurement. We measure the fidelity, measure the overlap of the final state with the initial state. And so we look at the information content as a function of the noise strength. Of course, if we're in the unencoded basis, then we would see that there's an exponential decay of information. If we're in the encoded basis, the information stays, it's unmodulated, and we could do any of our computations that we wanted in that basis. And we can nicely show that within these coded bases, it's possible to have a complete set of operators, and that you can rotate in these bases without ever leaving them. And that was part of the challenge of this process, is to always stay in that basis. Okay, now, it's very easy to think about these symmetries in things like zero quantum subspaces, where the symmetry preserves the state. But of course, that's not the only symmetries that we see in nature. And so you want to think about things that are a little bit more subtle. And I give you an example that if we thought about an error that, classical error now, that switched both of a pair of qubits. So imagine that I have two qubits, and the only error that happens is that both of them flip. If we did that, then we could code our information classically into symmetric and anti-symmetric subspaces, and the error would never mingle those. And so that we could save our information in essentially the parity of a set of states. And in this case, of course, the noise is not preserving the state. It's preserving the conserved quantity of the parity of the two joint states. Now, there are similar things that happen, of course, in quantum mechanics. And if I think about a three-spin space, my noise generator now is now going to have arbitrary collective noise, so that I have collective noise on three spins, but about an arbitrary axis. Now, so it's a little bit of a generalization from what we saw before, but now we don't find states that are preserved under this. But of course, if I look at the Lie algebra of that noise generator, it does not span the entire Hilbert space. And so there are conserved quantities. And the conserved quantities are j squared and jz. And so we can code our information in an operator. And then in this operator sense, we can preserve the information under this action, even though there are no states that are preserved under this action. And an easy way to think about this, I mean, here we should have Fano so he could give me a really easy way. But, you know, a not so hard way is just think about taking your first two spin 1/2 particles. You combine them into a spin 1 or a paired state. Add your third particle, and now you find that there are two ways of getting to this doubly degenerate spin 1/2 manifold. And so you could code your information in how did you get to this state. Did you get to the state this way or this way? And if you code the information in this path picture, then of course your error is not going to decohere you. You're always going to be in that same manifold. And so the states that you're going to code in actually look pretty familiar to you, probably. They're correlated states that are used quite frequently of having very similar to the so-called W states, which are maximally entangled 3-particle states. The W's are simply phase factors, multiplying those. Out of these 3-particle states, we have a logical qubit, which is where the information is going to be stored. And there's this additional spin over here, which is actually going to evolve under that error. Okay? So this is where our information is. That's where we're still going to have an evolution. The quantum code for implementing this is a little bit messy. I'm not going to go over it for you. Let me just show you that under this action, if we didn't code the information there, we would see this exponential drop-off. If we do code into this protected subspace, this subsystem, it's not a subspace, then with increasing noise strength, the fidelity stays the same. There's no drop. Now, of course, there is a big drop in the process of coding. And that's what you see there, that actually we have to do all this work and all this work over here to get in and out of that space. And we're honest about showing you, well, we really do lose some information by doing that because we don't have a beautiful quantum computer yet. We have our quantum information processor. But it's a wonderful subsystem in that it's independent of the axis of the noise. And so if I apply a noise along the x-axis, the y-axis, the z-axis, or I do those sequentially, or any combination of it, this information is always preserved under that. And so there's some wonderful opportunities of using symmetries, even if the symmetries are more complicated than what would be preserving states. I'm going to skip that. I want to show you one more thing here while we're talking about symmetries. Of course, entanglement is incredibly important in quantum information processing, and we can look at what happens as we try to differentiate 3-particle entanglement. Now, if we have 2-particle entanglement, everyone understands that. But if I have maximally entangled 3-particle states, they already start to get a little bit messy. What I've shown you here are the density matrix. These are experimental density matrices that we measure, where we've created a state which is the GHZ state. So it's a maximally entangled 3-particle state, 0, 0, 0 plus 1, 1, 1. Over here, we've created another maximally entangled state, the W state. You cannot go from the GHZ state to the W state directly. There are two different classes of entangled 3-particle states. But they are in each of these classes, these are the maximally entangled representations of those classes. If we look at a GHZ state, and I say, let's make a measurement. So I'm going to project out one spin. If I project it into the Z basis, then of course I lose all the entanglement. That's not surprising. If I project off into one basis, then we're going to end up with these two diagonal states. But let me project it now not into the fiducial basis, not along the basis of the axis of quantization. Let me make a projection onto the x-axis. And now, of course, we see that we have these two conditionally entangled states. I end up with two Bell states that are conditional on the state of the third spin. And so we can see the action of measurement on the GHZ state giving us either losing all the entanglement or, in this case, ending up with a conditional entanglement on the third spin. Now, of course, if I lost the information that I measured on that third spin, we would end up in an unentangled state. You have an entanglement that's conditional on your measured result of the third spin. If we look at the W state, and now I make a measurement of one spin in either the Z basis, the quantizing basis, or the X basis, in both cases we end up preserving entanglement. So the entanglement in the W case is actually less than that in the GHZ case, because regardless of which axis I collapse one of the three spins into, I'm always going to preserve some entanglement. And in fact, even in the case where I throw away that information that I recorded of the third spin state, we will still retain some entanglement in the W state between the remaining two particles. So the W state is, in one sense, more robust against particle loss, but it is less entangling of the three particle states than the GHZ state. Okay, so there was all sorts of other things I wanted to tell you, but I won't. Let me acknowledge the people that did the work. The quantum error correction, the noiseless subsystems, the decoherence-free subspaces is work of Evan Fortunato and Marco Pravia, with a lot of help from Nicolas Boulant. The quantum eraser work that I just showed you is work by Groom Teklemarian. My collaborators are Tim Havel and Seth Lloyd. And we do a lot of work with the people at Los Alamos. Raymond Laflamme is now at Waterloo. The take-home message I'd like to leave you with is that quantum information theory and quantum information processing gives you a new way of looking at quantum mechanics. And if you want to move through complex Hilbert spaces, it is a very useful way of thinking about the information content of your experiments and how to control and set up your experiments to achieve a particular result. Thank you very much. Sorry for the mess with the computer.